electronic configuration. Okay, and whenever this configuration is converting into excited state, it will looks like this one. Okay, the one electron jumps from the s orbital and move to the p1. Okay, so as we know that carbon form how many bonds? Four bonds. And what is the
Mm-hmm.
reason? Because there is four vacant orbitals. See, there is four vacant orbital which can gain one electron. Okay, so let's suppose
Mm-hmm.
now we are talking about carbocation only. How
Mm-hmm.
carbocation will looks and how it will form and what is the hybridization of carbocation. So firstly,
Mm-hmm.
see how many bonds carbocation have? Three.
Mm-hmm.
Okay, so these three, one, 2 and 3, these three will form a bond. Okay, and how they will form? One s orbital plus how many p orbital? Two p orbital.
Mm-hmm.
Okay, because there is three bonds na, so one bond from this, one from this, and one from this. Okay, so the total hybridization for carbocation will be sp2.
Mm-hmm.
Do you have any idea about this method? Or if you don't have any idea, don't stress about this, because we can calculate directly hybridization also from the bonds and the lone pair. Okay, but this is
Yeah,
a
yeah, yeah.
complete method.
That's
Yeah,
yeah, sorry, to interrupt. Yeah,
yeah,
that's the method that I'm used to use or doing.
the number of
Um,
bonds via calculation.
yeah, yeah.
Okay, okay, that will also fine. Okay, so that's why the hybridization of carbocation is sp2. Okay, and now as I am okay, so as I'm sharing you that the carbocation having vacant p orbital. So which orbital is working as vacant p orbital? This one.
Yeah.
Okay. So this orbital is working as vacant p orbital, and vacant p orbital we can represent like this. Done. So hybridization
Mm-hmm.
of carbocation is sp2. How many electrons it having? Six electron. What is the geometry of carbocation? Geometry or shape?
Planar.
Yeah, trigonal planar.
Mm-hmm.
Okay. And how we can identify the stability of carbocation? So 3-degree carbocation is more stable than 2-degree and in the end 1-degree. Okay. And what is the reason of carbocation's stability? So on the basis of hyperconjugative structures. So on the basis of hyperconjugation, do you know what is hyperconjugation?
Hyperconjugation is that overlap of orbitals?
Yes, yes. And in hyperconjugation, how we can directly identify that the given structure is more stable through hyperconjugation as compared to other?
I think the more hyperconjugation there is, the more stability there is.
Yes, absolutely. But like how we calculate the that the compound having more hyperconjugation?
Like if there's a double bond,
A
no?
double bond can
Triple
also,
bond?
and number of alpha hydrogens. Do you know alpha
Oh.
hydrogens? What is alpha hydrogens?
I think, oh, alpha and beta hydrogens. I'm not 100% sure.
Okay. So alpha hydrogens are basically any hydrogen. Let's suppose this is carbocation. Uh, Wait. Let's suppose this is the carbocation. Okay. And there is three groups attached to the carbocation: CS3, hydrogen, and hydrogen. Okay. So in this case, let's suppose this is the carbocation. Okay. And
Mm-hmm.
the carbon which is directly attached to this carbocation, that carbon is known as alpha carbon. So in this case, there is
Mm-hmm.
only one carbon attached. So this carbon is known as alpha carbon. Okay. And
Oh, okay.
yeah,
Yeah.
So,
Is
and the hydrogens which attach directly to the alpha carbon, those hydrogen known as alpha hydrogen. Okay, so as number of alpha hydrogen increases, the stability of hyperconjugative structure also increases. Stability will also increases. Okay, so let's suppose I'm giving you some examples. Okay, wait. Uh, mm, Tell me which structure is more stable? Uh, A, B, and C. Which structure is more
um
stable?
I would say the third one, C.
How? How?
Well, you said number of alpha hydrogens, right? Matters
Okay,
here.
so how many alpha hydrogens A have?
That are attached directly, zero, right?
Mm, the carbon which is directly attached to the carbocation, that is alpha carbon, and the hydrogen which attached to that alpha carbon. Let's suppose this is carbocation, and how many carbons directly attached to the carbocation? In this
One.
case, one only. Okay. So how many alpha carbons? One only. Okay. And now how many hydrogens this carbon having, the alpha carbon?
Which one?
Here, this
Oh,
in the structure.
there's one direct attachment, right?
One directly attached carbon, and how many
Mm.
hydrogens this carbon have?
Three
So
attached.
how many total alpha hydrogens? Three alpha hydrogens. Okay.
Yeah.
Now you tell me in case of A, how many alpha hydrogens A have?
Okay, so there would be three, six, nine.
Yes, absolutely. Nine alpha hydrogen. And in case of B,
Mm, seven.
how?
Wait, no, actually, no, sorry, that's wrong.
Yeah.
Six.
Yes, six. And then
Um, then I think three.
absolutely good. So the directly attached hydrogen to the carbocation is not calculated as alpha hydrogen. Okay.
Yeah.
Yes. So now you tell me which is more stable in compared to A,
Which
B,
one's
and C.
more?
In compared to A,
Um,
B, and C. As number of alpha hydrogen,
yeah.
see here above in here. As number
A.
of alpha hydrogen increases, stability will increases. So A is more stable,
Uh-huh.
then B, and then C. Okay.
Yeah.
Okay. So this is the stability order. Now do you remember the degree of carbon as we discussed in our first
Mm-hmm.
class? How we
Yeah.
calculate degree? Okay, so tell me that A is what A carbocation is having what sort of degree? Like is the carbocation 3 degree, 2 degree, or 1 degree?
The carbocation, I think it's carbocation. I think three
Yeah.
degrees.
Yes. Very good. So the first one is 3 degree, second one is,
Two. Yeah.
and the last one is 1 degree. Okay.
Mm.
So see, as I'm write down here that the hyper as 3 degrees more stable than 2 degree and then 1 degree. We also prove that, na? That how it will stable. Do you
So,
understand?
how do the? Oh, I'm so
Yeah.
sorry.
Yeah, yeah.
Sorry,
Ask.
did I interrupt you?
No issue.
Oh,
Ask me. Yeah.
no, I was gonna ask. So, how does the degree of the carbon matter in terms of stability? Is it like, yeah? How does that matter?
So the degree of carbon is Like we can direct the degree of carbon term we are using, because if in case, let's suppose if examiner asks you directly, okay, so in that case, via the use of degree of carbon directly you can answer. You don't need to calculate the alpha hydrogens and all. Okay, so that's why we are using 3 degree, 2 degree and 1 degree. Because if I'm not define you that there is the stability order via the use of 3 degree, 2 degree and 1 degree, you can proceed with hyperconjugation. And in hyperconjugation case, you will calculate the total number of hydrogen, then after stability. Okay, while in case of degree of carbon, directly used to define stability. Okay, you can say that there is two method. The first one is degree and the another is hyperconjugative structures. Okay, so which is more preferable? If in case you are able to directly give the answer via the 3 degree, 2 degree and 1 degree, that will also help. Okay.
Mm.
Yes, this is the one thing, and the another thing is that the 3 degree, 2 degree and 1 degree, these carbon are also stable by the use of hyperconjugative structures. Okay, 3 degree, why 3 degree is more stable, why 2 degree, why 1 degree? As 3 degree is having more alpha hydrogens, 2 degree as compared to 3 degree less, and as compared to 1 degree it is more. So there is via the both hyperconjugation and degree of carbon we can explain the stability.
So the reason why A is more stable is because there's more degrees and more hyperconjugation together.
Yes, yes. We can say that more degree or uh, more hyperconjugation.
Okay.
Okay. Okay. So this is about carbocation. Now let's suppose I'm giving you. Okay, I'm giving you some example of SN1 reaction. Okay, let's suppose there is a reaction. Can you write down the all the steps in the reaction which is involved? This is a SN1 type mechanism. Okay. Wait a second. Okay. Do you understand the question?
Wait, sorry. Let me just look at it again.
Yeah.
So like what would the potential products be? Or how the reaction takes place, right?
Yes, and which is more feasible or which is more stable, and which is giving
Okay.
more stable product also.
This is for SN1, right?
Both are assembled.
Both are SN1.
Yeah.
Okay. Uh, oh, I see. I can tell that the first one is going to be more stable.
Why?
Um, the carbon is has more degrees,
Yeah,
and there's more hyperconjugation.
absolutely. And in second one?
Mm,
First one
I
is
mean,
mhm,
there's some hyperconjugation, but
yeah.
the degrees are less,
Yeah. So the
right?
first one is
Yeah.
3 degree, second one is 2 degree. So three,
Mm-hmm.
the product A will be more stable as compared to product B.
Mm-hmm.
Okay. So that's how we identify the SN1. And now you tell me one more thing that in case of SN1,
Mm-hmm.
okay, in case of SN1, what sort of product we are getting? Is the product is racemic mixture or inverted product or the same product?
For SN1, it's a racemic, right?
Yeah. How? What is the
Because
reason?
you can attack.
Yeah,
Yeah, I
and suppose
remember
I'm. Mhm.
you mentioned this in the last class. It can the nucleophile can attack the p orbital in either direction, front or back, right?
Absolutely, very good. So from both direction, nucleophile can attack. So that's why we are
Mm-hmm.
having a racemic mixture. While in case of SN2, we are only having
Mm-hmm.
Walden inversion. Okay, that inversion is known as the Walden inversion. So we are getting only Walden inversion in case of SN2. And also Walden inversion because in case of SN2, we can direct only attack from the back side, not from front side. Okay, so there is only one possibility. So there is a complete 100% mixture will form. Okay, and let's suppose if I'm doing a backside attack, so the product will form that is a diastereomer or an enantiomer. What sort
If
of
you're sorry, can you repeat that?
in case of SN2, what sort of order what sort of product will form? Is it a diastereomer or is it an enantiomer? Or it depends upon the reaction.
Reaction?
Yes, majorly it
Mm-hmm.
depends upon the reactions, and
Mm-hmm.
in some cases it will an enantiomer. Okay, because the completely inverted product we are getting, and that is used as a mirror image. Okay, so do you know the difference in between enantiomer and diastereomers?
Vaguely. I don't know if I would be correct though.
Okay, okay, yeah, no issue.
I think enantiomers, are they like a complete mirror image?
Yeah,
Yeah, okay.
and do you know the CIP rule?
So
R and S
CIP.
configuration.
I'm sorry, can you say that again?
R and S configuration. Absolute configuration.
Yeah, I've heard of it. Yeah.
Okay, okay. Okay. So do you have any doubt from this one in carbocation and how SN1 will proceed? If not, then we
Um,
are moving to the absolute configuration portion.
um,
Yeah.
like,
Do you have any doubt in
uh,
your basics? So we will firstly discuss that because that is more important as compared to anything now. Because the basics are,
yeah.
yeah. You can ask me.
Um, I was just like wondering like because I think like in the last class we talked about aromaticity. So what's the main link between aromaticity and I guess this topic, or is this completely separate from aromaticity?
Aromaticity. These are the two different topics. Firstly, okay. So aromaticity is used to identify stability. Aromaticity
Mm,
is generally belongs to the general organic chemistry. Okay, but that is a very most a very important topic. So that's why I take this topic. But this is not
mm.
interrelated. These topics are not
Oh,
interrelated.
okay.
Okay.
Okay, okay. They're completely
Yeah.
separate.
Yeah. Yeah.
So for stereochemistry, as far as I remember, it has a deep relationship with the reaction mechanisms, right?
Yes. Stereochemistry has.
Yeah. Like this, it's very interrelated with this topic, right? SN1 and SN2.
Yes, SN1 and SN2 both needed. Like, do you remember when we discussed 3D representation?
Yeah, I was gonna ask if you can do some more examples of that. I think I would like to
Sure,
see
sure.
that. Yeah.
Yeah, 3D representation and Fisher representation. Both of them are very useful and
Mm-hmm.
they are used in a reaction mechanism most of the cases.
Okay.
Okay, while the 3D representation is
Mm-hmm.
the most important part in that. Okay, let's suppose we are going to do some 3D examples. Okay, okay, let's suppose I'm having. Now you tell me from where I can see that this molecule, from which direction I will see this molecule.
Is it gonna be towards where 3 and 4 is?
Yeah, absolutely. I'm putting my eye in between 3 and 4. And if I need this into present into Fisher, so how I'll write? Where is 3 and where is 4? Is it in left, right,
Mhm.
top, or bottom?
I think it would be top. Top would be dash, right?
No.
Was not dash, I'm sorry, wedge.
Yeah. Tell me.
3 and then 4 would, yeah,
3
4 would
here, 4
oh.
here. Okay. And 1 and 2. Done. Okay, let's suppose I'm giving you one more example.
So why
Mhm.
I thought it was the opposite, like for the
Opposite
Fisher
for.
diagram. Like I thought 3 and 4 were gonna be top and bottom. Is not
See,
not right.
we can do that also. But let's suppose if I'm seeing from this position. Okay, let's suppose I'm.
Okay.
So the 3 is out of the plane or in the plane? 3 and 4.
Outside the plane.
Yes. And above the plane, 3 or 4? Which one is above the plane?
3, right?
3, absolutely. So 3 is above the plane as compared to 4. Okay. You take a 4 pen and putting those 4 pen in the same in the same manner as the first compound will proceed. Okay. So firstly, what you'll do, the carbon is in the middle, and you'll take 2 pens which is in the same plane. Okay. Firstly, do that. Take 2 pen and add their last part, and both the pen are in the same plane. Okay. Then add one pen which is above the plane and another pen that is below the plane. Do this thing by yourself. Then you will, I think then in that case you will understand me.
Okay.
Okay.
One pen above, one pen below. Uh, what's hmm. Like what would be towards myself? I'm sorry, like what
Wait a second.
in the plane. 1 and 2 are in the plane, right?
Yeah, 1 and 2 are in the plane, and the two are completely opposite.
Yeah.
If Wait a second, I'll share my screen again. Okay. Is this visible to you?
Mm-hmm.
The 3D structure of methane.
Mm-hmm. Mm-hmm.
Okay. So now do you understand like how the methane will look exactly? Okay,
Mm-hmm.
so wait, I note that. Okay, so let's suppose these two are in the same plane.
Mm-hmm.
Okay, and this is wedge form, and this one is the dash form. Done. And if I'm watching this molecule from here, okay, and I need to annote this. So how I will do that these two are, see, if I'm seeing from here, these two are the top and bottom. Let's suppose I'm first one, second, third one, and this will be fourth. Okay, so which is on top side?
One.
One. Now you understand now why I'm using one here, then two, then three here, and four.
Oh, this is a tetrahedral, right?
Yeah, this is tetrahedral.
Oh, okay.
And
Would it help for me to visualize the shape of the molecule then, like the
yes, yes.
vesicle?
Um, because in this case, this is the only tetrahedral. If I'm having pentagonal and in case I'm having a double bond or pi star molecule, so you needs to identify each molecules by yourself. Okay, let's suppose I'm having more molecule. Wait a second. Mm, there is not any molecules which is having pi bond. Okay, so no issue. In stereochemistry, majorly the CH4 or tetrahedral will come majorly. Okay.
BH3 and tetrahedral. Okay. For organic, right?
Yes, majorly organic.
Mm-hmm. Okay.
Yeah. So now you
Okay,
understand.
then that
Yeah.
makes it easier then, because if there's
Yes.
only like two of them, then you can visualize it, right?
Yes.
Like,
Yes. Yes. I didn't have a website. There is a website which is very useful. That is the American website. Homes like I didn't remember its name exactly. If I'm getting that, I will share that website with you. That is also very useful to identify each and every molecule.
mm-hmm.
Okay. Okay. So let's suppose now I'm giving you some more example. Mm. And you try by yourself. Okay. Now you tell me in the second one where I put my eye on the second one.
Where it would be where the F in chlorine, or yeah, F in
Wait,
chlorine.
yeah, F including. And how I will represent is F come on top.
Um, Hold on. No, I don't think so, right?
So wedge and dash are generally come on which direction? Is it they are on top or bottom, left or right? At which position?
Mm.
Tell me.
I think on the other example they were left and right, right?
Yeah.
We did.
So in major cases, they are coming on left and right only. Okay. So
Oh,
fluorine,
okay.
chlorine, hydrogen, hydrogen. Okay, and in this case, yes, three,
and
hydrogen, methyl, and ethyl. Okay. Oh, sorry. Okay, some methyl and ethyl coming here, and CS3 and hydrogen. So in this case, I'm putting my eye on here, and which is on top, methyl, and which is on
mm-hmm.
bottom, it will ethyl. Okay, and let's suppose if examiner will ask you in the first, let's suppose this is the first one. Okay, and examiner will ask you that if the compound is 3-degree halide, so in that case, what type of reaction will occur? Nucleophilic substitution. Okay, and what will be the product in case of the first example?
Mm, can you repeat the question?
Let's suppose this the first organic compound which is written. What sort of reaction it will give if it is a 3-degree compound, 3-degree halide. Okay, and that is the first question. Tell me answer for that. What sort of reaction it will give if it is a 3-degree halide?
3-degree halide. I think SN1.
Yeah, was SN1. And what will be
Yeah,
the major product? Is the product is racemic or
it would be racemic, right?
yes? So let's suppose
Mm.
if I'm having R nomin. Do you remember R and S?
Yeah,
A little bit about R and
a
S.
little bit.
Okay. R and S
Yeah.
are basically used for specify optical activity. If the compound convert the light into right hand side or clockwise or anti-clockwise, on the basis of that we will differentiate the compounds R and S. Okay. So let's suppose this is the organic molecule, and the reagent is in the R form. Okay, and through SN1, and there is SN2. Okay, so in case of SN2, is the R configuration will change or not?
For SN1,
Yeah.
um, our configuration, I think it would, right?
So in case of SN1, we are having both probabilities, na? It can attack from
Uh-huh.
top and bottom. So in the case of SN1, the product will be R, 50% of R and 50% of S. Then this type of these type of arrangement or possibility is also known as racemic mixture. If the mixture having 50% of R and 50% of S. Okay.
Mm-hmm.
Okay. And in case of SN2,
SN2 would be all R, right?
how? In case of SN2, we
Mm.
invert the compound. Na?
Oh, we invert it, right. So then S
Yes, in majorly
completely.
in case
Okay.
of S. Okay. Any issue, any doubt up to now?
Yeah, I don't
Yeah.
know why I think I've like struggled with this in the past too, like when I took OChem 1. It was like the visualization of the wedge and dash was a little hard, I think.
Wedge and dash. Okay.
The we're like yeah, and doing the Fisher and Newman I think was a little
So this
difficult.
is the only Fisher form, this one.
Mm-hmm.
Okay. If you
Yeah.
proceed, if you trying some example,
Mm-hmm.
so in that case, maybe you will help.
Yeah, maybe you can give me some homework or something.
Okay,
Practice.
okay. I'll give you some homework.
Because Fisher is like easier. I think Newman was a little bit more complicated or something from
Yeah,
what I remember. Yeah.
yeah. But and also Newman is not as much useful because it give complication in reaction form.
Yeah. I
Yeah.
remember it came up a lot though, and like on my syllabus, like it came up a lot.
Do you have a Newman in your syllabus?
Yeah, when I took it at my previous college, it was like very, very heavily tested, I think. Especially
Okay.
towards the end of the semester, I think I remember that. It was tested a lot. I think maybe in, I don't know, because I think in America, like there's a more emphasis on Newman, I think.
Yeah, maybe it's possible.
Yeah. But for Fisher, so when you say that you're observing from a certain direction, like what does that mean? Like sorry, I know this sounds really dumb, but like, like for
No,
example,
no.
for
Ask me.
for the first example, like when you're observing from 3 and 4, does that mean you're looking directly how like
Yeah,
oh, I see. I see now.
yes, you need to understand like
Okay.
what sort of concepts I'm using. Like if I'm standing in between 3 and 4, let's suppose I'm standing in between 3 and 4, okay? So 3 is
Mm-hmm.
above the plane, okay? And
Mm-hmm.
4 is below the plane. So let's suppose
Mm-hmm.
I'm standing in between 3 and 4. So above the
Mm-hmm.
plane means on my left hand side, if I'm standing over there, so my left hand side, there is the 3, and on my right hand side, there is the 4. Okay, and which is upside, the first one is on the upside and the second is downside. Okay, if I'm standing here, you understand that if this is a 3D molecule and you are standing over there,
Mm-hmm.
don't understand?
Yeah, so
Yeah,
so I can see how 1 and 2 would be in the plane.
yes. M- that's why I'm
Yeah.
sharing the screen to see that there is two bonds that those are the same in the plane. And if you are like if you are having any issues, you can directly note down that whenever two elements or two molecules are in the same plane, they are on the top and bottom. Okay,
Mm-hmm.
and portion you can write on the third one and dash on the fourth position.
Mm-hmm.
Okay, see this one, the second one. Wedge is here, dash is here always, and the atoms which are in the same plane are top and bottom. Wedge, dash, top and bottom. The third wedge, dash, top and bottom. Sorry, wedge here, dash here, and this will be top and this will be bottom. Okay, if you are having any issue to imagine
Mm-hmm.
a 3D structure, you can directly go through with that. Okay, you can write down that if same plane in same plane, then they will on top and bottom. Okay, in
Mm-hmm.
wedge form, they are on the left side, and in dash form, they are on the right side.
Mm-hmm.
Then
Yeah, I think the tool
this will
you
move.
showed me was pretty useful.
Which one?
The website, I think that was useful because I was able
Okay,
to
okay,
see
okay.
the molecular geometry. So I think
Sure,
If
sure.
you see the like if you're
Yeah.
able to see the geometry, then it's easy to like
Yes,
see like
yes,
what where
yes.
you're looking. Yeah.
I'm
Yeah.
sharing the link here over here.
Okay, thank you so much.
I'll also share this website to the ninjas. Okay.
So the molecules will either be trigonal planar or tetrahedral, right?
Mhm.
In these
In
reactions.
yes, yes, in organic chemistry, we are
Okay.
majorly going to deal with these only.
Okay, that's really good to know, like for me.
Yeah.
So yeah.
These are also very useful
Mm-hmm.
in when we study about reaction mechanism. Okay. So, can we do some questions on absolute configuration?
Okay, yeah.
Okay. On R and S.
Mm-hmm.
Okay. Why we are using absolute configuration? What is use of absolute configuration?
Oh, sorry, are you asking me or
Yeah,
I thought
yeah,
I
I'm
didn't.
asking you. Do you have any
Oh,
idea?
for abs I think it helps us understand what kinds of products we would get or like how the molecule looks during a reaction. I don't know. Different stages of the reaction.
Mm, yes, majorly we are using to like identify the polarity of the substance, majorly. Polarity or what sort of changes a reactant will proceed in a reaction. Okay, so let's suppose in absolute configuration, we are starting with R and S configuration. R and S configuration. Okay, and R and S configuration will define by CIP rule. What is CIP rule?
Mm, CIP, I'm not sure.
Wait a second. Wait a second. I think my marker is not working. Okay, CIP rule is given by a scientist on and on the basis of their name, we are name that rule by CIP rule. C represent here corn, I represent here in gold, T represent here prolog. Okay,
Mm-hmm.
these are the scientists' name. And okay, so let's suppose I'm asking you this structure, the first one structure. Okay, so in the first one, there is the name I written first, second, third, fourth. I'm giving some numbering. Are you able to see that
Where?
in the first one?
The numbering? Oh yeah, yeah.
Okay. So, in CIP rule, what we are going to do, We just rotate these numbers by anti-clockwise or clockwise. How? Let's suppose I'm having, let's suppose this is the first one, and this is the second one, and this is the third one. So what I'm going to do, we are taking an arrow from the first up to second and then third, okay? Like this. Okay, first, second, and third are the major, and we are going to use that on this can be clockwise or anti-clockwise. So tell me, this arrow represent clockwise direction or anti-clockwise direction?
The arrow clockwise?
Absolutely. So whenever the representation is clockwise direction, that molecule shows R configuration, and if is in anti-clockwise, it will be show S configuration. Okay. So firstly, there is some rules. Okay, so right here. The first rule. So the first rule is priority. Let's suppose I'm having this one group. Fluorine, fluorine, and hydrogen, and bromine. Okay. So before that, you also needs to know that in case of absolute configuration, we need all the four groups. See, there is four groups now. So all the four groups needs to be different. Okay, if there is two same group, in that case, we are not going to use this method. Yes or no?
Okay.
You understand? So we need all four groups are different.
Mm-hmm.
And then as I'm giving numbering above. So how I'll give numbers to this one? Like how I'll take hydrogen first or fluorine first or chlorine first numbers. How I'll
I
give
think
numbers?
atomic number.
Yes, yes. Priority means as the atomic mass increases, the priority of any group will also increases. Okay. So as atomic mass increases, atomic mass increases, the priority will also increases. Okay, that is the first rule. Okay, I'm giving you some example. So, in case in this one, fluorine, chlorine, bromine, and hydrogen, which one having first priority?
I think it would be bromine, right?
Yeah, and second,
Chlorine.
yes, and this will be the third, and this will be the fourth. Okay, now the major
Mm-hmm.
part will come that there is two possibility. One, two, three, four. Okay, there is two possibility that fourth group can come on these two direction or on these direction. Do you understand? Fourth,
Um, yeah.
fourth group. Like there is four possibility of fourth group to having a position in a Fisher form. There is
Mm-hmm.
only four possibility. Okay, so if the fourth group will come on these two direction. Wait a second. the fourth group is on these two direction, in that case, answer will be same. And in these two cases, answer will be going to change. Answer means you will understand how it will work. Okay, so let's suppose first you need to represent this wedge dash into Fisher.
Mm-hmm.
So how you will change? Tell me. Here is
Um,
fluorine will come.
hmm?
Fluorine will comes to here. And on this position, chlorine. Yes or no?
Yeah.
Do you remember I told you that wedge on left side, dash on right side, and then hydrogen, and here is bromine.
Mm-hmm.
Any doubt up to now?
No.
Okay. And bromine is having first position, then chlorine, then fluorine, third one, and this will be the fourth one.
Mm-hmm.
Okay. So now we mark a arrow and see that the compound is clockwise or anti-clockwise. So first, second, third, and fourth. Okay. So the compound is clockwise or anti-clockwise?
Um, why am I don't know. Anti-clockwise.
Yes, it is clockwise. So clockwise means it will be R, and anti-clockwise S. Okay. Now what we are going to do, we will see that this is clockwise and this the product is R configuration, R having R configuration.
Mm-hmm.
Okay. Now we are say cross check these with last these possibilities. Okay. So fourth group is on upside or downside. Here is the fourth group. See?
Mm-hmm.
Okay. So from the below portion, do we need to change our answer? So fourth group is above side. So this will be
Mm-hmm.
our option. Okay. So answer will be the same. So in the end, the R is same and the product will be R configuration. Do you understand? Now you will do by yourself. Okay. I will give you some examples. Okay. So generate a question. Okay. I will write down the question. Okay. I'm using this pen. Hmm. Are you able to see the question?
Yeah.
NH2, CF3. This is CH3. And here it's CH2Cl. Firstly, convert this molecule into the Fischer form.
Okay. Um, let's see. Into the Fisher form. So where would I write?
Yeah.
And then okay. Let's see. So mhm.
Are you representing CH3 and CH2Cl in a corrective way?
Mm.
Wedge on left hand
Oh,
side?
sorry.
Yeah.
So, oh, H. Uh, is this correct?
No, you are
I
doing
thought,
in same way. CH
uh, oh, my God, I didn't
we-
even know I was doing the same way.
wedge form will be coming to here.
Oh, okay, okay.
So
Yeah, I
CH,
think I made a mistake with the wedge and
here
dash.
is CH2Cl. No issue. Now you'll solve. Now give numbering to each one.
Um, Numbering, let's see. I think this one probably. Or no, fluorine, CF3, let's say, right? And
No,
then,
see, first, okay, wait a second. Firstly, you will see that which atom directly attached to the carbon. In case of NH2, in case of CS3, in case of CF.
oh, okay. Oh,
Okay.
right, right. So then it wouldn't, okay, it would be this one. Um,
Yeah,
and
good.
then, and then amongst, and then
Yeah.
okay, yeah. And then after that, if
Yes,
you look
yes,
what's directly attached
yes.
between the carbons, then it would be this one.
See again,
Like,
which is more heavier, like which is having more mass as compared to fluorine and chlorine.
yeah, wouldn't it be fluorine?
No, it's chlorine. Chlorine is
Oh,
having more atomic mass, okay? So it will be second. First and second. Then which is third and which is fourth?
I think this, the one with fluorine would be third, right?
Yeah.
Yeah. And then lastly, this one.
Yes. Now represent arrow here.
Uh, Arrow?
No, like this first, second, third.
Oh, sorry.
Yeah.
Uh,
Okay. So is this clockwise, anti-clockwise?
it would be clockwise, right?
Yeah, clockwise, and then R or S? R.
Yeah.
Clockwise is R. Now we are saying that okay. Okay. So from R and fourth group on which side? Fourth group is on here. Here is the fourth group. Okay. So fourth one is in the left side. So do we need to change our answer? Hmm?
I'm not sure.
Okay. So firstly, erase your this one. Okay. See why this these things these things. So fourth group is on left side. So this will our case. Okay. And in both these cases, we need to change our answer. Okay. So
Hmm.
R will be converting into S, and that is your original configuration. Okay, I'm giving you one more example. Mm. Okay, let's suppose now I'm giving you a direct Fisher representation. Here is NH3. Here is hydrogen. Here is Ci3, and here is deuterium. Now numbering this one.
Number, okay.
Yeah.
Uh, what's D? Is that D?
Yeah. D
The
is
bottom?
deuterium. Deuterium. It is isotope of hydrogen. It is having
Oh, okay.
yeah.
I would honestly need to look at the periodic table because I don't remember all of the atomic numbers.
Okay. No issue. Deuterium is having more mass as compared to hydrogen.
Oh yeah, okay, yeah.
Yeah.
It comes towards the end, right, of the periodic table?
It is in the same.
No.
It is in the same portion where hydrogen is, because all the isotopes
Oh,
are in the same position as the atom will.
deuterium. I'm like trying to find on my periodic table. What element number is it?
Deuterium
Atomic
is
number, sorry.
one.
One is deuterium?
Yeah, hydrogen and deuterium both is having one number. So which is more
Oh,
heavier as compared to hydrogen and deuterium? Deuterium. Okay, and deuterium is having more weight as compared to hydrogen.
oh, because in my text, I'm like looking at a textbook. They don't have deuterium with hydrogen.
Yes. They doesn't represent deuterium in periodic table. No
Oh,
need. Deuterium is having more priority as compared to hydrogen. So
okay.
if hydrogen is in the fourth position, deuterium will be in third position.
Mm-hmm.
Okay. And now NH3 and CH,
Nitrogen would be first, right?
hydrogen, yeah. And
Yeah.
this will be second. Now represent arrow like this.
Yeah.
Yeah. Clockwise or anti-clockwise?
Anti, right?
Yeah. Anti-clockwise means it is S. Okay. And fourth group is on the right side.
Mm-hmm.
So we do we need to change? Fourth group is on right side. See, answer needs to be changed.
Changed, yeah.
Yeah. So S is converting into R. So R will be our answer. Done.
Mm.
You can ask me if you have any doubt. Do you have any doubt from this one?
Like this problem?
Yeah. You need to solve some questions.
Yeah. Hmm?
You need to solve some questions. After that, you'll find.
Yeah, I just need more practice.
Yeah.
Um,
I'm
I
sharing some questions with
okay.
sir, and they'll share to you. Okay, some textbook questions by
Okay.
end of the class. Yeah. And like,
Um,
yeah.
yeah, here I don't think for the last problem I had any like questions. Um,
Okay.
so I just wanted to like, or I guess I did want to ask something. So for when you're looking at like when you're trying to number the different elements or yeah, elements, you would look to see the first common, right?
Yeah.
Okay. I
That.
because I think I messed up
Mhm.
on that when I solved the first question. I wasn't paying
Yeah.
attention to whether it was like
You
yeah, the
calculating the total mass, like overall, you are
atomic.
saying. Yeah. The first one we are going to calculate. Okay. In next class, we will solve some more questions. The questions related to, let's suppose if there is some rings will come in the Fisher form. So how we are going to deal with that? And some double bond, if in case double bond will come, if in case cis and trans will come. So like how we understood these questions. Okay. So we'll do those questions in next class, and I'll share some. Uh, practice problem that is like a basic practice problem. So you'll do by yourself. Okay, and if you have any doubt, you'll ask me in next class.
Okay.
Okay. Do you have like do you want to take a screenshot for this one, or you note it?
No, I want to take screenshots, yeah.
Okay. So firstly, you will take by starting of class. Uh, okay. So from here you can take.
Okay, you can move down to the next portion. Sorry, can you reveal the title? Yeah.
Carbocation.
Okay. Yeah. You can keep going down now.
Okay.
Okay. And then to the next part,
Yeah,
please.
this will be the next one.
Okay. And then, yeah, and then after that it was the last part, right? Or, oh no, sorry.
Okay, you can take this.
Okay.
Then.
And then, yeah, and then you can go down again.
Sorry.
Okay. And then there was like a last example.
Then.
Yeah.
Okay. Okay. So if you have any doubt, you can ask me now and in further class also. Okay.
Okay.
Yeah.
So, wait, SN1s are. So for SN1 and SN2, will we cover like what sort of nucleophiles or electrophiles are favorable or leaving groups?
That we will cover in the halide part when we discuss each functional group in detail. Okay. Uh,
Oh, okay, okay.
yeah. In this
For
case,
SN,
yeah, because in stereo, we only needs like what sort of direction the nucleophile will attack, from which direction. Okay, we'll discuss each and every step of SN1 and SN2, leveling effect, and all of solvents, nucleophiles, electrophiles, which is major and which is feasible towards SN1 and SN2, all of that. Okay, when we discuss functional group in detail.
oh, okay.
Yeah.
So the stuff that we're learning right now, this is all still relevant to us, like SN1 and SN2, right?
Yes, yes, these are relevant.
Um,
Yeah, because these are basics. So in SN1 and SN2, those reactions are not only coming into the SN1 and SN2 portion. There is a lot of reactions in each and every functional group. Majorly, each and every functional group shows nucleophilic substitution. So in that case, I'm not like giving you a brief about SN1 and SN2. There is stereo in between any part. So that's why I'm discussing here only. So you are able to understood that how the reaction will come, how we can represent a 3D molecules into 2D or Fisher. Okay, these are very basics. So whenever we need these portion, we will do.
okay.
Yeah.
So what we covered with absolute configuration and then Fisher projection wedge and dash, so that shows us like how the molecule will change when these reactions happen, right? Like
Yeah,
physically, when
yeah,
it goes on physically. Okay.
yeah. And one more thing that these are also used to identify enantiomer and diastereomers. We
Oh,
will
okay.
discuss that in next class, like how we
Yes.
identify that given compound is enantiomer or diastereomer with the help of these configurations.
Okay.
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 Okay. So we'll meet in next class.
Okay, ma'am. Thank you.
Bye.
Bye-bye.